Today's video is about differentiation. How and why does differentiation work, and basically that. Now this is for addition mathematics, but you can leave the video after I explain power rule, because up till power rule is 0580. After power rule is the add math stuff. So after this 81st page, you and those who are doing 0580, they can leave. So let's get into differentiation. What is differentiation? It is defined as finding the rate of change using a formula or the explanation and rate of change. It is rate of change. Now I did say watch Essence of Calculus. If you haven't, then you must. But you can be here. Now the notation for differentiation is this. This is the operator. When we do this is the operator. When we apply this onto a function, how do you apply it? We just apply it like so. Like how you apply, like you have 4. If we say apply the function f, we surround this by the f. When we say apply the derivative around a certain expression, we say to add this on both sides and then evaluate. Now here the remaining, I have told you what these are, basic rules. But why are these rules like this? What does it mean by rate of change? Well, let's say you have a curve and you want to find a tangent on there. How will you find it accurately? Well, you will try to sample 2 points. One should be this, the point that you want your tangent to be on, and another point on the curve. This will give you the most best approximation. Why? This does not look like it right now. This does not look like it, but as you creep towards this point, if you can see my cursor, if you creep towards this point like very close, then we may get a better and finer approximation of the tangent till we converge to a point. Converge means boil down, land at a point, definite value. For the gradient, the equation itself, good luck with that. Coordinategeometry. That is how the tangent is found. Now, how is this defined? Well, since this is only 45th, this is only at maths, I won't get too much into higher level stuff, but you need to know what a limit is. Limit basically lets you approach a value safely, technically. So if we say we want to find a limit as x approaches 4 of the function 4x. What does this mean, approaches? Meaning as we creep towards this value of x, as we creep towards this value of 4, like this point is our value of x. As we creep towards this, what is this value going to be? Now normally it will be defined, just plug in 4 and boom, 16. It will creep towards 16. But this is also useful for values which we cannot directly plug in. Example, a famous example is sine of x over x. Now this has an asymptote at x is equal to 0. But what if you want to go towards 0, right? So how do you do this? Well, there are methods to evaluating the limit. I am not going into that. But just so you know, a limit is you creep towards a value safely. You do some shenanigans to fix the this so that this is in a form where where if you plug in the value and the variable approaches, then it will be a value. Okay, now one more thing. Okay, there's another thing I want to tell you. When it does reach a value, okay, okay, if the example, this is equal to 1, trust me, okay, this is equal to 1, this, we call this limit to exist. Okay, so that means if this works out, meaning this limit exists. There may be other cases like limit as x approaches 0 of 0 of x to the x. This does not exist because this approaches a value, okay, 0 to the 0, which is not agreed upon. Okay, this is the example. Enough of that goofy up. I want to tell how does this tie up to the derivative. This ties up to the derivative by the example of the point creeping towards x. Now this is our point x1. This will be our point x1 plus h. If as each approaches 0, as each goes smaller and smaller, as each x plus h goes nearer to x1, by this term being 0, this should give us a good curve, a good tangent. Okay, now what is the formula for the gradient? It is y2 minus y1, x2 minus x1. What is our first point that we sampled? The first point we sampled is x, f of x. So we plug in this f of x, x. What is the second point we sample? The second point we sample is x plus h, f of x plus h. Nice. Now we will write this like so, x plus h and x plus h. The denominator simplifies to h, and this is our thing. Now we said as h approaches 0, so this means we take the limit as h approaches 0, and this is the definition of the derivative of f of x. Taking the derivative of f of x leads us to this definition. Okay, now since we got this tool, this will let us explain the other functions. Why does taking the derivative of that function lead us to getting the answer that we have here? Okay, so whenever I say this thingy, this entire explanation I did, this is called the first principle. Okay, meaning the derivative is defined as the limit, okay, as this limit. So I will resort to this for explanation, okay, when needed. Okay, first is the basic rules. Okay, the first rule is the derivative of a constant is 0. Why? Because if we go here, okay, like example, this is the constant graph. Okay, we sample the points this and this. Now the height will f of x is c. There is no x that the function controls. So if we plug this into a limit definition, this is c minus c over h, which is 0 over h, which is 0. So as a limit as h approaches 0 of 0 is 0, because there is nothing to control other than just spit the value out. And another thing, okay, if you guys do not understand that, you guys can see that we move by h, but we rise by 0. So this is rise over run, which is inevitably 0. Easy, right? Good. Differentiating a sum is the same as the sum of the derivatives. Now this for the first principles, I do not know how to do this. Okay, but this is this exists because you know that this function, when we add two functions together, f of x plus g of x, they and their y value, okay, when we have 2 points, okay, 2 points, example, this is, okay, these two are the x points, our function is this and our other function is this. One point, one curve will be like so, the other curve will be like, example, exponential. When we add these two together, they will produce another third function. Get me? Another third function. This function basically is the addition of these two values. If we add these together, then what do we get? We get the value, this new function h of x. When we do this, when we differentiate a sum, the same as differentiating the sum of the sum of the terms. Okay, this, yeah. So if we apply the derivative on here, it will be the same as applying the derivative on here as well. Get me? Okay, good. So now, okay, I did this prime thingy. What is this prime? I said the prime is also a notation. Okay, here I will supply both definitions using the prime notation and the derivative notation. Okay, every time. Okay, so it is only between which cup of tea you choose. Either you choose the fraction notation or the prime notation. Okay, I forgot who made these notations. There's also a third notation, third notation, okay, which is used by physics people, but it's like an A-level physics or something. We only worry about these two notations. Okay, the prime notation and the fraction notation. I personally use the prime notation, but you can use other notations as well. Power rule. Differentiating a term ax to the n, where a and n are constant, gives the derivative of this term yields this. Why does this occur? Why does this, happen? Let's figure it out. So we have here h, and we have sampled these 2 points. And this point here is ax to the n, and this point right here is ax plus h to the n. Right? Now we want to find the slope. Okay, the slope of our function is ax to the n, and we want to find the tangent at this red point. So how do you do? We want to find the limit as h approaches 0 of ax plus h to the n minus ax to the n all over h. Okay, now there will be conflict on how I write my symbols, so I'll try my best to not be confusing. Here, okay, this, remember, h approaches 0. Okay, this term, this point goes creeps towards here, so the tangent will also get better and better. Okay, so this is how we do it. We need to manipulate this to get rid of h in the denominator. That's all our trick. Okay, that's what we will be doing in our video, just doing some algebra. We can expand this. This expands to a times x to the n plus n choose 1 of x to the n minus 1 each, plus so on. And if you have gone to the series chapter, then you know what I am talking about. Okay, ax to the n. You can see something. These two terms can be cancelled out. Exactly. That is why we have expanded this. These two terms go bur. So this is like so, all over h. Another thing you can notice here, if I add a second term here, dot 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 dot, dot, is every term now contains an h. We do not have to worry about terms without an h. So we can factor out an h over here. Do. And we can see this these h's cancel out. Wow. And finally, we do not have an h in a denominator. We can safely put 0 and replace h as 0 and continue forward, because now if we did earlier, then this would give us a undeterminate form, unfortunately, which makes this limit not exist. But when once we have removed the h in the denominator, we can safely plug in 0 and find this limit. So since these all terms have an h remaining, these all terms will vanish as we plug in 0. Now n choose 1, this is the same as n, so this is simplified to n, and voila, what do we have here? The same output. We proved why this works, and we can now spam it any way we want. This go brr, okay, plug and play, blah blah blah. We do not have to worry about, take this for granted. Moving on. Now I have continued power rule to be to function to work for any input. Now the input here, okay, yeah, this is you can read all this. This uses a thing in calculus, the chain rule. I do not want to prove the chain rule. Okay, I will only prove the initial bit. I do not want to prove the chain rule. I may later. Okay, you or just find another video. Okay, so this area, what does this say? If you are given a function to the nth power, function f of x raised to the nth power, not, okay, remember this is function raised to the nth power. Okay, this is not the same as saying f of n x. This, what does this mean? This means the taking the nth derivative of f. Nth derivative of f. We do not want to take the nth derivative of f, please. So yeah, so differentiating this guy, what do we get? So if we differentiate, okay, what do we get? We get the power rule. Sure, power rule with, instead of x we have f of x, and we need to multiply by the derivative of f. This is what the chain rule states. What does the chain rule say? That if we have f of g, a composite function, and we are taking its derivative, then what we get is you have the derivative of the outer function with the inner function as the input, multiplied by the inner function's derivative. So following this is what we get. This is what we have to do, unfortunately. These shenanigans. Okay, so if you ever get something like differentiate this inner function, okay, we can have this inside here, no worries, but we have to multiply by the derivative of this as well, and you of course have to be careful about the brackets. Here I didn't put the brackets, my bad, but it's generally not needed, but you should, as a good habit, and to not be confused what you are doing in each step. And as I said, I will both provide the fraction notation and the prime notation for every function. How to deal with multiplication and division of two functions? This is where product rule and quotient rule comes in help. These two are also in the syllabus. It states that, okay, given that f and g, the functions f and function g are such that they make up the function h, where each function h multiplies these two functions, you can use the product rule to differentiate this. If we differentiate this product, what do we get? We get multiplication, this multiplied the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. This looks a bit weird. I write it like this. Okay, and I said this is usually done with UV. Addition and multiplication is commutative, so there may be variations. The quick setup is to FG and differentiate the outer functions like so. If you understood this part, then congratulations. Okay, here is a use also. Here we have two functions, function f and function g. Here we differentiate the first function. I think we did a misprint. Okay, misprint. This should be -2 here, not 5. Okay, sorry. But yeah, this is the first function derivative times the second function plus the second function times the first function times the derivative of the second function. Doing all our work. Okay, here I differentiated this bit and then this bit, and I multiplied it all together to get this junk. Yeah, this weird abomination. You guys can simplify it if you guys are brave enough, but I will be busy proving this, why it works. Why does the product rule work? Well, let's go and do it ourselves. So we have f of x plus h, g of x plus h, minus f of x and g of x all over h. Now our goal is what? To remove h from the denominator. You may think, no, this these are dependent on the value the functions f and g. No, we can do this generally. Okay, why do you have to be very specific, come on. How do we even do this? We will do something very weird. You may not like it, but you may later on. You will add and subtract a term. What do we add and subtract? Well, we will add and subtract f of x, g of x plus h. You can do this for f of x plus h, g of x. I'm gonna go with this. We will subtract this as well, g of x plus h. Why do we need to subtract it immediately? Well, to not change anything. Okay, next we will factorize this whole line. Okay, we will factorize this whole line. Doing so, we get what? Well, these first two terms have g of x plus h in them. So we will do f of x times times f of x plus h plus f of x. And we also have this. What is common in here? F of x. So we add f of x. We will get g of x plus h plus g of x. Sorry, we will do this negative here. Now this is all under what? All under who? H. We can split our fractions in like so, yada yada yada, boom. Now this is all under our limit. We can break this limit into two limits thanks to this this fraction thingy. Let's deal with this first. Okay, now here I have done a little mistake. This is a plus, but we can fix this by switching factorizations and getting this f of negative term here. Next, we can also have the same argument for this as well, and this will be plus like so. If we refactorize, okay, with minusing first and adding first, you will get this result. Okay, yeah. Now let's do our limit as h approaches 0. If we plug in 0 here, this will become a g of x. Nice and good. What about this multiplication term? Do you recognize something? This is the function f prime, derivative of f. So if we do our shenanigans with here, given f was something, then we can show that this is indeed f prime. And so taking the limit, then this will become g of x. Similarly, if we do same, this will become g prime of x. Adding them together, we get f prime of x, g of x. Why? Because the multiplication is commutative, remember. And here f of x times g prime of x. Wow, we proved this. Very easy, right? That's one uncomfortable bit of adding and subtracting a weird, oddly specific term. Don't ask me how I know. Now, the quotient rule. We want to find the derivative of a ratio. How do we find the derivative of a ratio? Let's plug it in and see. This is f of x plus h, g of g h plus h minus f of x, g of x all over h. I do not like the top. I will multiply everyone by what? G of x plus h, g of x. Any problem? No. Why? Because this is the same case. This will get divided out later on, blah blah blah. So fixing this, what do we get? This we will get f of x plus h, g of x minus f of x, g of x plus h all over h times g of x, h times g of x plus h times g of x. Nice. Now here we can do some stuff. If we let h go to 0, this won't look very good for us. So we will do some. Do you see some similarity here? This looks a bit awfully similar to how we did the multiplication, but now it's a little different, and we will do something different also by adding and subtracting some terms and then simplifying further. We will add and subtract f of x plus h times g of x plus h. If we do this, f of x plus h, g of x plus h minus this term f of x plus h, g of x plus h. This looks a bit, like, yeah, a bit messed up, but I'll fix it. Wait, if we factorize, okay, if we group these two terms, we'll get f of x plus h times g of, no, we will factorize, I can't decide, negative g of x plus h plus g of x. And then you can factorize also this other term which has g of x plus h common. I will do this with a purple, hollow purple, giving us now both have g of x plus h as the common and have one more thing as common, f of x, f of, so here this one would be f of x plus h minus f of x. You may be getting to why and what am I doing here. This all under these terms, this term that we have in the denominator earlier. Now what do? Some magic transformation. Paste. Now, okay, let's look at these limits individually. This looks like negative version. Okay, if we factor out a negative over from here, you get the definition of g prime. So you can substitute in g prime, and we get that if we let x approach 0, we get g of x, this term squared. If we see this is the definition of f prime. So this will be f prime. If we let g approach, h approach 0, this will be such g of x squared. Now the denominator is the same, so you can combine, and if we fix everything together, we will get what? F prime g of x minus f of x. Oh my god, f prime of x g of x minus f of x g prime of x all over g squared. Voila, this is indeed the definition of the quotient rule. See, carbon copy, very easy, Now you then need to obviously take this for granted. You aren't going to solve this. Okay, moving on. Trigonometric functions, exponential functions, and logarithmic functions. These are going to be a bit fun to do. Okay, because these are these functions that you already have defined earlier in the book. Sine, cosine, tangent, secant squared, cosine, logarithm, exponentiation with base e, etc. All fun and games. So let's continue. How do we do these? These I will do for sine. These will be the same for cosine, given sine of x is equals to cosine of 90 minus x, or some shift in x minus 90 or x plus 90, etc. Cosine is just a shifted sine function, So I will differentiate the sine function using first principles. Limit as h approaches 0 of sine of x plus h minus sine of x h. What do we get? Well, let's see what we can fix. This looks in compelling, like we should do something with this. Indeed we can. This is not in syllabus, but this is required for the proof. where sine of of sum of a of b is equal to sine of a cosine of b plus cosine of a sine of b. Going further, x h sine of x cosine of h cosine of x sine of h. Now using this you can slap it in like so, minus sine of x. You can factorize sine of x in the first term. Sine of x minus 1 like so, all over h. Now these two terms are all over h. Limit as h approaches 0. How do we go further? We know we have to do something with this h term. Okay, this factors out. Sine of x factors out, and cosine of x factors out. How do these help us solve our problems, solve world problems? Well, does it need bit? You don't, because proving them would need a bit more brain power. Okay, and we are hopefully using this. Now I can simply simplify for this. Sine of h of h. Why? What does this converge to? What does this give us? Well, do you know the Taylor expansion of sine? Yes, you do. The Taylor expansion of sine is sine is equal to x minus x cubed over 2 prime plus x 5 to the 5 prime blah 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 blah. The signs alternate and there are x to the odd power divided by a odd factorial. These all have this x in them. You can factor out this x. This is x 1 minus x squared, x fourth, blah 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 blah. This, okay, since this is sine of x over x, this x cancels out and we are left with this series dot 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 dot. Now plug in h. This is the same as sine of h over h, so h is this all stuff. Now take the limit as h approaches 0. What do we get? We get that sine, that these all terms collapse. These all terms become 0 because h approaches 0. These all terms become 0. What are we left with? We're left with this 1. 1 isn't governed by h, so it is equals to 1. Now for this this has a similar stuff going on. Cosine of x is equals to 1 minus x squared over 2 prime plus x to the 4th over 4 prime, and so on. This is now the sine function with even x. Let's do some shenanigans. Also, here we want to factor out this one on the other side. We shift it on the other side. Next, we divide by x. What do we get? This 1, 3, 5, so on. If we plug in h is equal to 0, we can safely say this all is equal to 0, because every term has an x, here, and when x is replaced by 0 as h approaches 0, this all turns into 0. So this limit is equal to 0. Okay, we factored out the sine of x. So the sine of x is also kash. So we are left with only cosine of x. That's why this converges to cosine of x. For cosine, this is a little similar, but you guys can probably do it like I have here using the Taylor series. Tangent, just use the the quotient rule. We can actually use the quotient rule for this one. Since we have defined quotient rule, defined sine, defined cosine, we can do this easily. Sine over cosine, taking the derivative of this, what do you get? We get sine prime cosine minus sine cos prime over cos prime over cos squared. Now sine prime is cosine and sine cosine, and cosine is negative sine, and negative positive. What is the top simplifies to 1? Why? Because of identities. Now this is cosine squared. What is cosine? We can use indices to bring the squared outside. So this is 1 over cosine. What is the 1 over cosine? Secant. So secant squared is our answer for tangent, for the derivative of tangent. And if we have a function as the input, these will need to multiply by the derivative of the inner of the input function. Yay. And same with trig of n. Okay, if we have this. Now this does not work. Okay, if we differentiate this, and yes, it needs this, but we won't really need to do this. This is very out of course. Logarithms. I love logarithms. Do you love logarithms? Well, you must. After seeing why does taking the logarithm of x gives us 1 over x. Yeah, it does not even give us the exponentiation or another logarithm. It gives us a polynomial. Weird, huh? And it's the same thing. Integrating 1 over x gives us a logarithm. What? Why? Let's see. Why does this happen? So this will be log ln of x plus h minus ln of x all over h. This x can be put now. The sum of the logarithms. Okay, what does this mean? When we have no, never mind. We can simplify this. Wait, let me remember. You guys remember the difference of two longs is the same as the log of the ratio of the inputs of the here. So we can simplify this, giving us x plus h over x. Now we can simplify this further, giving us 1 plus h over x. This all under h. Now this is h, and okay, from the back of our hands we one day remembered natural log of 1 plus x gave us the series, the infinite sum x minus x squared over 2 plus x cubed over 3 blah blah blah. It is the same as the series, okay, the sine cosine series, but with alternating and not using factorials. Now we want to somehow get 1 plus x. Here we wish to remove the x from the denominator. Why don't we just keep using this? If we replace this with h over x, then you see this is h over x squared, blah 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 blah. You guys get the point. In all of them, they have the h. So what do? We can factor out this h. Yeah, that's a very fun bit. So if we do over h, this gives us this expansion. 1 over x squared of so this was h 1 over so h squared x cubed blah 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 blah. If we let h approach 0 now, this all will collapse to 0, and we left with 1 over x. Very easy, very easy. And you can just instead take this for granted, and if f of x, and if the input is a function, we of course multiply by the derivative. For the exponential e, it also uses the Maclaurin series, the Taylor series. Okay, yeah, I know this all is just cheating using Taylor series, but polynomials are the best, man. You cannot argue with a polynomial. Okay, they are the best. They are what you have been doing your entire life via algebra. Okay, they are the most easy to factorize, most easy to work with, most easy to solve. This is why we love polynomials. Okay, and like to express everyone in polynomial form. This also abuses the fact. Now here we use in the index properties to factor out e to the x from here h, and from outside the limit. And as you called it, this will turn out to be is equals to 1 because of our shenanigans, blah blah blah. Factor out e, divide by e, this, that. The first term would be h of this. The first term of this would be 1 minus 1. So the first term is h, divided by h. The first term is 1. Set is everyone 1 to 0. This will be 1. And so e to the x times 1 is what? E to the x. And finally we prove this also. I hope this was fun to see how people did all of these. Okay, we can still do this by just cheating and looking and seeing the nature, like how does it function when we do this stuff by using like experimental method. And that is very slow. We love doing equations. We are lazy people. Mathematicians are lazy. Like, subscribe and share if you understood something. Okay, if you liked the proving of these and may have helped a part of your brain asking why are these like these are. Okay, so yeah, apply differentiation, you guys can get it. Tangents, easy. These are from my admat note, from my normal notes. Okay, and literally I edited these to be a little different, to be a more exaggerated. I had them a bit closer so they look like I was just drawing random lines. So I fixed them to be a bit more outside, a bit more apparent, a bit more obvious. Okay, these derivatives. Okay, you guys can read what I have on the screen. Rates of change, example, small change in here, and yeah, this is turning points from my notes. See, this is the same diagram I used earlier. I know I'm not very original with my things. It is literally the same thing. Sketching curves, and this is also okay. I might make a sketching these applied differentiation video if you guys subscribe. Please, I need subscribers to get to 200 at least. Just a small favor, 200. That's all. I hope you like today's video. Like, subscribe, and share. Bye.